Isomorphisms are nothing more than a specific type of homomorphism. So we learned about isomorphisms first, right? And now we're learning about homomorphisms, which are more general. But what's the difference? What did we say last time is the difference between a homomorphism and an isomorphism? So the big difference between homomorphism and isomorphism is that isomorphisms must be one-to-one and onto. They have to be bijective functions. Homomorphisms don't. But what do they share in common? The operation, preserving, respecting, whatever we want to call it. So homomorphisms that are bijective are isomorphisms. But both of them share this product property, phi of x times y, operation in the domain, is equal to phi of x, operation phi of y, operation of the range. So that's something that both of these things share in common. And I want to kind of draw an analogy that I don't know how many bells it's going to ring for you, but it might. So in linear algebra is about the study of vector spaces and linear transformations on those vector spaces, right? And we just so happen to get wrapped up a lot in linear algebra thinking about matrices. But the only reason we like matrices is that they give us a computational tool for understanding linear transformations of vector spaces. And so in linear algebra, the role of linear transformations is the role that homomorphisms is playing for us in abstract algebra. So linear transformations of vector spaces. And there are some linear transformations that are also one-to-one and onto that are bijective. Did we have a name for those in linear algebra? I don't know that we all agree on a name for them. Because I don't think there's a one-word answer. Rather, there's invertible linear transformations. So those matrices that have an inverse matrix that we can compute represent invertible linear transformations. So in abstract algebra, the same role that isomorphisms are playing for us in abstract algebra, invertible linear transformations play for us in linear algebra. Right? They're just functions that respect the operation, the structure of the spaces on which they're acting. Now, what was it in linear algebra that made a linear transformation a linear transformation? What did it have to satisfy? What is it that makes a function on a vector space a linear transformation? Scaling and adding. So two things had to be true. That the transformation applied to x plus y as vectors, I'm going to write little hats over them like they're vectors, has to be equal to what? T of x plus t of y. That looks an awful lot like this, doesn't it? Right? But then there was one other requirement, right? T of, you said scaling. What does that mean?
So Cx multiplying a vector by a scalar.
Multiplying a vector by a scalar, what has to happen there?
The C pulls out.
The C pulls out, right. So the scalar, the T acting on a scalar multiple is the same as that scalar multiple acting on the image. So both of those things had to be true. Now the scaling doesn't really look like the homomorphism kind of property, right? Because inside of these parentheses is a vector and a scalar being smushed together. And those are two objects that are very different in kind one to another. As opposed to up here, x and y, these are elements of the same group, right? So they inhabit the same world as one another, and we're smushing them together with the operation of that group. So this kind of is not similar to our homomorphism property, but this one very much is. And what we can say, I sort of highlight that property right there. What we can say is that a vector space, linear transformations on a vector space, every vector space, it turns out, is a group. It's a group that has more structure than just a single operation, but a vector space is a group. So V, which is a group under addition. So plus is the operation here. So that algebraic structure that I get by taking a vector space and just adding vectors, so forget about the scalar multiplication, just think about adding, that forms in a group. Not only a group, an abelian group, because addition of vectors also has the commutative property. And this statement here, that the functions that we care about on vector spaces are those that respect the addition operation, right? Addition on the inside, addition on the outside. Those are the functions that we cared about in linear algebra, the linear transformations. And so the same thing is true in abstract algebra. The only functions that we care about in group theory are those functions that respect the operation of groups, namely they have to satisfy that the function applied to a product, quote unquote, is the product of the images of those two elements. But there were consequences in linear algebra to this analogy. One consequence is, what do we know from linear algebra for any linear transformation? What happens to the zero vector under a linear transformation? It has to stay the zero vector. For any linear transformation, t of the zero vector equals the zero vector. But why? So why did that have to be true?
Is that because of the identity?
Oh, identity. Say more about that.
So,
Alexa says that this sounds an awful lot like the property that we knew to be true about isomorphisms in abstract algebra, which is every isomorphism sends the identity element from the domain to the identity element in the range, right? Yeah, this sounds exactly like that, because the role that the zero vector plays inside of a vector space is it is the identity element of the additive group of vectors. Right? Because if I add 0 to any vector, it remains that same vector. Right? And we can actually use that additive property to prove that t of 0 has to be equal to 0. After all, what do I get when I add the zero vector to itself? I get 0. But then if I apply t to both sides of this equation, on the one hand, I get t of 0. On the other hand, I get t of 0 plus 0. But what can I do to this expression? I can simplify it by using the fact that t is a linear transformation. It respects the operation of addition. In other words, it's a homomorphism of the additive group of vectors. And therefore, I can break out this addition into t of 0 plus t of 0. So t of 0 plus t of 0 is equal to t of 0. But now what? Now let's just subtract t of 0 from both sides. Use the cancellation property in the additive group of vectors. Right? And when I do that, what do I find out about t of 0? T of 0 has to equal the 0 vector. Yeah, exactly. So all we had to know about t was that it respects the addition operation in the additive group of vectors. That was enough to guarantee that t of 0 must be equal to 0. But that's true not just for invertible linear transformations. I didn't use the inverse of t in this argument at all. All I used was this operation preserving property. So what do you think is true about t? Even if it's not invertible, a linear transformation will still send the 0 vector to the 0 vector. So, and come back to Alexis' statement. What do you think we can conclude, therefore, about homomorphisms and isomorphisms? What would be the analogous statement here?
Both of them will send all 0 or the identity element to the identity element.
Yes, right. So we already knew that isomorphisms sent the identity to the identity, but now I think we can see why every homomorphism also sends the identity to the identity. Phi of the identity element of the group G is equal to the identity element of the group H. And we could use the very same argument as I used over here for vector spaces to prove this theorem. But rather than me do that, I'm going to let you have this in your notes, and that's going to be one of the things you're going to work on proving in one of your groups today. So here's a function which takes a symmetry of the square and sends it to a permutation of 4 symbols. And the rule for doing so is that it takes any t, any of my reflections, and it just kills it, makes it the identity. And it takes any rotation, my single rotation generator, and sends it to the 4-cycle 1, 2, 3, 4. So just as an example, for this function, what would phi of tr squared be? Or no, let's do tr to the 3rd. How would I figure that out? First of all, let's assume that phi is a homomorphism. And when I say assume, it's actually that assumption that lets me define phi as simply as I have here. I'm defining what it does to t and what it does to r, and then I'm saying what it's going to do to any other element is we're just going to define that it's a homomorphism. And so phi of tr to the 3rd power is going to be equal to what? How would I simplify that if I know that phi is a homomorphism? Yeah, it's phi of t times phi of r cubed. And 5r cubed can be written as 5r quantity cubed. Right. And both of those equal signs here are applications of the homomorphism property, HP, the product rule. Okay, and now that we know what phi of t and phi of r are by our definition, phi of t is the identity, phi of r is the 4-cycle 1, 2, 3, 4 raised to the third power. Now we can just plug in what we know about how to simplify products of permutations.
We also, it's inverse?
Yeah, it is. For in the case of a 4-cycle, yeah, for any 4-cycle, its third power is the same thing as its inverse. So yes, 1, 4, 3, 2 would be phi of tr cubed as an example. So this thing is a homomorphism. And what I'd like to know is, what does this tell us about the structure of these two groups? How many elements are there in D4? How many symmetries of... So what this homomorphism is really doing for us is it's blurring, it's making us blind to the difference between the identity element in D4 and the reflection, T, in D4. We no longer see the difference. And because we can't see the difference between E and T, we can't see the difference between R and TR. We can't see the difference between R cubed and TR cubed. Those are both going to go to the same place. 1, 4, 3, 2. And R squared and TR squared. We haven't actually figured out where those go. Let's do that real quickly. What's T of R squared going to be? Sorry, phi of R squared going to be? Yeah, phi of R quantity squared. So it's the 4-cycle 1, 2, 3, 4 to the second power. And in that 4-cycle, the second power, 1 is going to take 2 steps to the right. So 1 is going to go to 3, which is going to take 2 steps to the right and end up at 1. So 1, 3. And then 2 is going to take 2 steps to the right and end up at 4. 4 is going to take 2 steps to its right and end up back at 2. So we get a product of 2 transpositions, 1, 3, 2, 4, as the image. Okay. So now we kind of know what this homomorphism, what this function is doing to all the elements of D4. And most importantly, what it's doing is it's causing us to be blind to the difference between E and T. Now, E and T, together, as a subset of D4, are furthermore, what else? What other relationship can we say that E and T have to D4? Besides being a subset, what are they? They're right. So there are a couple things. They are the kernel. So there's a $5 word for today. The kernel of this function, this homomorphism phi. What makes it the kernel of phi? It's everything that's getting sent to the identity. That's the definition of what we mean by kernel. Right. Kernel of phi is the set of all G in the domain, which in this case is D4, such that phi of G is equal to the identity element, which identity element is the empty permutation in this example. So it's everything that's getting killed, quote unquote. I know it's a violent metaphor, but I can't resist using it. Everything that is getting killed by this homomorphism is called the kernel. Okay. So that is E and T. It's the kernel of phi. What relationship does it have to the group D4, do you think? First of all, is it a subgroup? Is E and T, the set consisting of E and T, a subgroup?
Yes.
What's a quick way to tell?
It's just it's like the trivial subgroup.
Well, E by itself is the trivial subgroup, but E and T together? How do we know that's a subgroup? Since D4 is a finite group, what does a finite group subgroup test tell us we can check? Just check that it's closed. Closed plus finite equals subgroup, right? According to the third subgroup test. So how do we know that E and T together make a closed subset? E composed with itself is E. E composed with T is T. T composed with E is T. T composed with itself is E. T composed with itself is E. So that's every possible product we could make inside of that subset. They all remain inside the subset, so it's closed. So this is a subgroup. If I call this K, then K is a subgroup of D4. Okay. But we also waited a long time to introduce kernels because they're not just subgroups, They're what kinds of subgroups? Leading question of the day. They might just be normal subgroups. They might just always be normal subgroups. So at the end of our last class, I posed this metaphysical and slightly off-color question. Where do normal subgroups come from? Right? And the answer wasn't that they get flown in through the window by a stork and dropped in your lap. They come from homomorphisms. But this is how they come from homomorphisms. So to any homomorphism that I can write, I can associate with that homomorphism a normal subgroup of the domain of that homomorphism. And this is how. That the kernel of a homomorphism out of a group is always a normal subgroup of that group. Regardless of the group, regardless of the homomorphism. And that's important because normal subgroups are our building blocks for groups. Right? If I can understand enough about the normal subgroups of G, then I understand how G is put together. What's it made of? How is it constructed from smaller pieces? And so this gives us a really powerful tool for understanding that normal subgroups can even exist. And if I want to search for them, I can do that by searching for homomorphisms out of our group. Last question then. What, in this picture, is the factor group of D4 by K? So D4 mod K. Where do I find it in this picture? First of all, what are the elements in a factor group? The cosets of my subgroup, my normal subgroup, right? So my elements are the cosets of K.
Are they? Okay, yeah, sorry.
So where do I find the cosets of K in my picture?
Go down the column.
I get one coset for each row of this little table that I've just sketched over here. Right? So D4 quotient K has how many elements? How many rows? How many cosets are there?
4.
There's 4. There's one for each row, right? So there's 4 elements in this factor group. And I could call them, well, if they're cosets, that means that they can be represented as something times K. Since K was a normal subgroup, let me ask the following question. If I'm looking at this element here, which is this second row, I could write that as R times K, right? That second row, RK. But what about KR?
Because it's normal, we already know that it's the same thing.
If it's normal, which you're taking my word for it right now because we haven't proven it, but if it's true that K is a normal subgroup, then KR and RK are the same thing. So it doesn't matter. We could choose left cosets or we could choose right cosets. And because they're cosets, we can choose any of their representatives that we want. We could have called it TRK instead. But just for simplicity, let me call that second row RK. Oops. RK. R squared K. R to the third power K.
So is a factor group defined for something that's not normal?
It wouldn't be a group. That's the issue. If the subgroup weren't normal, then we would still have the set of cosets, but we wouldn't be able to define the operation on cosets in a coherent way. Okay.
Yeah,
So
that D4 over K, though, that can't be used for notation for a
We-
similar idea for something.
for a non-normal subgroup, yeah, we wouldn't, because we want that to represent a group and not just a set. If you wanted a set of cosets, you might use a different notation for it, but we don't usually study those anyway.
Okay.
So this is a group that has 4 elements in it. And to what 4-element group is it isomorphic? This is how I want to wrap up here. What does this group look like? It's K, RK, R squared K, R to the third power K. When I multiply any two of these together, like if I took RK times R squared K, what would I get? I'd get R cubed K, which is the same as R inverse K. Yeah, sure. Because when we have a normal subgroup, their cosets multiply in the same way that any element of those cosets multiply, and therefore the representatives of their coset multiply. So R times R squared is equal to R to the third. So what can you tell me about this factor group? It's got 4 elements in it. Is it abelian?
Yes. It's also cyclic.
It's cyclic. And what's a generator for it? RK. Exactly. RK is the generator for this group. It's a cyclic group of order 4, so what's it isomorphic to? Z4. Cool. There we go. So this is like we're getting to that galaxy brain level of the meme now, right? Where we figured out what subgroups were, right? So we could say something about subgroups. We figured out what isomorphisms are, how they work. We figured out what normal subgroups and cosets look like. We now know what homomorphisms are, but this is like a grand unified galaxy brain theory of how all this stuff fits together, right? If I want to understand the group D4, this homomorphism can help me to do it. Because by figuring out what this homomorphism is doing, figuring out the kernel of this homomorphism gives me a normal subgroup. And then I can figure out that that normal subgroup has cosets, and this group of its cosets are isomorphic to Z4. And so in some way, by the way, what group is this subgroup isomorphic to? What is K isomorphic to? Group of order 2 is K cyclic. Can we write every element of K, this first row here, as a power of something? Yeah. What's its generator? T. So it's a cyclic group of order 2. So it's isomorphic to Z mod 2. And so what we've just kind of justified for ourselves is that D4 is, I'm going to put the word like in quotes here, D4 is like a product of Z2, that's my normal subgroup, by Z4, which is the factor group. It's like Z2 is playing the role of the first row, Z4 is playing the role of the columns, and I'm just going to write and here in the middle of Z2 and Z4. So there's some way in which we can put Z2 and Z4 together to make D4. Right? That's kind of what we learned here.